everyone. My name is Wan Juan Park. I'm from Chungnam National University in South Korea. Today I come here and show you our study, which topic is experimental numerical study on supercavitating flow, induced vibration and noise. There are 5 parts will be included in my presentation. There are literature review, objectives, experimental setup and numerical method, results and discussion, and conclusion. Now let's get started. Firstly, I'm quickly introduce what supercavitation is. According to supercavitation generation, the supercavitation can be divided into natural supercavitation and ventilated supercavitation or artificial supercavitation. Firstly, the natural supercavitation can be obtained by increasing speed or increasing pressure. However, ventilated supercavitation can be obtained by injecting a non-condensable gas into the low pressure region. According to the advantages of ventilated supercavity, some applications of ventilated supercavitation such as torpedo, or scamper, or Korean torpedo. What about the physical aspects of natural and ventilated supercavitation? The natural and ventilated supercavitation are identical or the same cavitation number when the Froude number, Reynolds number, and Weber number are equal. In this study, we use the sigma V stands for the natural cavitation number, and sigma C stands for the ventilated cavitation number. For the ventilated supercavitation, there are 2 parameters we need to consider. They are ventilation coefficient CQ and Froude number. For the case of ventilated supercavitation, under the low Froude number, the tails of supercavitation goes up due to the gravity effect. So you can see this figure. Related to ventilated supercavitation, in 2017, Ann and his members conducted an experiment to investigate the characteristics of supercavitating flow. By measuring pressure inside supercavity, they did observe that in the state of forming cavity, the pressure inside supercavity increased significantly with the ventilation CQ. However, as soon as the clear supercavity is generated, the pressure inside supercavity kept almost unchanged. By another experiment in 2019, Yang and his members conducted another experiment to investigate the effect of body shapes, including light for bodies and cylinder for bodies. And the results showed that the cylinder for bodies require more ventilation gas to generate a clear supercavity compared to the blunt for bodies. In 2022, by another experiment, we investigated the effect of cavitator shapes, including cone-shaped cavitator and disc-shaped cavitator. And the results showed that the disc-shaped cavitator require more ventilation gas to generate a clear supercavity compared to other cone shapes of cavitator. Furthermore, by measuring pressure inside supercavity at 2 different positions, PC1 is located in the wake region of cavitator, PC2 is located in the real part of supercavity, and we observed that the pressure measured in the real part of supercavity PC2 is consistently higher than that measured in the wake region of cavitator, and the results are consistent with other cone shapes of cavitator. In 2023 latest study, we applied the calculation method to investigate the effect of angle of attack of cavitator, and the results show that with further changes in angle of attack of cavitator, it has significant effect on the supercavity length. You can see that. And also from numerical results, we observed that the closer mode migrates from the twin vortex to quad vortex when the angle of attack changes from -10 degree to -15 degree. Related to hot gas supercavitation, in 2022, we conducted an experiment to investigate the high temperature gas, and the results showed that the high temperature gas, about 1000 degrees Celsius, it has considerable effect to reduce the supercavity length fluctuation compared to normal temperature gas. By applying numerical method, we observed 3 distinct regions inside supercavity, including the hot gas ventilation effect region, the internal battery layer, and reverse flow region. And also we observed the temperature distribution inside the supercavity. In general speaking, until now, most of study related to ventilated supercavitating flow has been conducted just focused on natural or ventilated conditions. However, there are some gap knowledge they didn't consider the vibration or noise. So this study aimed to investigate the characteristics of supercavitating flow under both natural and ventilated conditions. The objectives are including the vibration induced by supercavity and effects of ventilation and to reduce the vibration, and also the hydroacoustic characteristics and also interaction between the ventilation air and also vaporous gas. And this is the schematic of cavitation tunnel we use during experiments, as well as the test model. The test model including the induced cavitator with diameter is 15.8 millimeters. And also we have 4 ventilation holes to inject the air for ventilated supercavitating flow. During experiment, we conduct experiment for 3G velocity changes from about 8 meters per second to about 13 meters per second. For ventilation experiment, we inject the air with a ventilation coefficient from 0.02 to 0.16. And this is the computation domain. The computation domain is designed corresponding to experiments. And also you can see the boundary conditions. We apply the velocity inlet and also pressure outlet and nose words for the test model and the calculation words. Right, then next here is validation part. In order to show, to check the verify of the numerical calculation, we compare our results with the experiments for 2 cases of natural forming cavities and ventilated forming cavities. So you can see that under the same flow condition of root number and also the ventilation rate, the experiment and also numerical calculation, the CFD results, they are good agreement with the experiments. Now let's come to results and discussion part. Firstly, I would like to show you some high-speed video from experiments. During experiment for one cavitation number, for example, this case is 0.72. We conducted 3 cases: the ventilated case, the natural cavity case with the pressure decrease, and the natural cavity with the we increase the 3G velocity. So you can see that under the same cavitation number, the cavity profiles are consistent among 3 testing cases. And also you can compare the natural and ventilated case. Under the same root number, the natural cavities induce more vibration compared to the ventilated case. And the results are consistent with other cavitation number. And this one is for 0.52. For the stage of supercavitation, you can see that also the same result with the forming cavity. The supercavity profiles are consistent among 3 testing cases. However, except for the gas naked region for ventilated case. And also you can observe that the vibration seems to be disappear among 3 testing cases, even for the natural supercavity. In order to show the result qualitatively, we use 2 parameters: the cavity length, Ls, and also the maximum diameter of cavity. So I can see that under the same cavitation number, the result between the cavity length and maximum diameter ds, they are consistent among 3 testing cases, and also they are good agreement with the previous work from Kim 2020-2013. So from now on, I will show some results from the calculation. Firstly, case A and case B is corresponding to natural and ventilated forming cavities. And case C, we combine both. It means that the ventilated case under the natural cavitating conditions. So you can see that for natural and ventilated, they are consistent with profiles. However, for the case of combination, we can observe that the region Z, and also there is a coexistence of both vaporous gas, it means blue isosurface, or the ventilated gas, it means the red isosurface. In order to investigate the hydroacoustic characteristics of forming cavities, during the numerical calculation, we apply the first William Hawkins acoustic model. In order to investigate, we measure the residual fluctuation at this point. So from the result, we can see that the natural forming cavity and also the case of combination, with introduction of ventilation air, it can reduce the peak values, also the magnitude of the subpressure level compared to the natural forming cavity. And also, we compare with the resistive case, we can see that also the introduction can reduce the peak values and also the magnitude of sub-resonance level. For the supercavity stage, in this result, we can see that that is supercavity evolution according to physical term. You can see that at the beginning, the ventilation focused only on the ventilation hose. But as soon as the clear supercavity is aerated, the ventilation air is red colored, focus on ventilation hose, and also is the gas leakage region. It's due to the gas leakage mechanism for the ventilated supercavity. And also, this result shows the ratio distribution inside supercavity corresponding to the physical term for the calculation. And about the hydroacoustic of supercavity, so also the same with formic cavity. With the introduction of ventilation air, it can reduce the peak values or also the magnitude of the sub-resonance level when compared with the natural supercavity. So finally, there are some conclusions from our study. Firstly, for identical catalytic number, the supercavity profile remains consistent for both natural and ventilated cavities, except for the gas leakage, as I told you before. Second, the introduction of ventilation air leads to the distinct reduction in the vibration and hydroacoustic characteristics. And third, for transparent supercavity, the distribution of ventilation air, the focus around the ventilation hose and also the gas leakage region. Meanwhile, the vaporous gas is dominant and concentrated in the mid region of the supercavity. This is all for my presentation. If you have any questions, please do not hesitate to let me know. Thanks for your listening.
Thank you. That was a wonderful presentation. Do we have any questions?